All right. So electron configurations are things that we've been doing for like 3 chapters already. We learned how to do this like back in chapters 4 and 5. And so we need to I'm just going to spend like a couple minutes reviewing. So what I want to do before we even start any of this process about talking about ions and why ions form and how they form is to maybe spend some time doing electron configurations for the elements here in the second period. All right, so for lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So what I want you to do over here on the left-hand side, right, we're going to, and I'm using my ruler. You could use some straight edge. Just going to draw a line so we can put some titles over there. And I'm going to start by writing the word atom. And let's see, I'm going to write lithium, and I'm going to leave 2 spaces, and then I'm going to write beryllium, leave 2 spaces, and then boron, leave 2 spaces, carbon, leave 2 spaces, nitrogen, leave 2 spaces, oxygen, leave 2 spaces, fluorine, leave 2 spaces, and neon. There, you can see that the entire thing on the screen, right? Perfect. All right, now, underneath that, what I want us to do is to come up with the electron configurations for these atoms, and we may as well do this in noble gas notation, right? There's no point in doing this with the long form, like from the 1s1 box. So let's do the next line down, electron config. And what I want to write is the electron configurations for the neutral atoms, right? So you remember how to do that? In noble gas notation, right? So what do we do if we want to read lithium? We start, no, in noble gas form. You start with brackets with what noble gas? With helium, right? And then you start reading from helium. Once you've read from helium, then what? To get to lithium, it's 2s1. What about beryllium? What would the configuration be for beryllium? Helium, 2s2. And boron would be helium, what's that? 2s2, 2p1. And carbon? What would carbon be? P2, correct. And then nitrogen, what would nitrogen be? Helium, 2, I wrote neon, bad girl. 2s2, 2p3. All right, and then oxygen, what would oxygen be? Helium, 2s2, 2p4. And then fluorine? What would fluorine be? Helium, 2s2, 2p5. And then what about neon? What would that be? Helium, 2s2, 2p6. Nothing new, right? You knew that. Okay, fantastic. Next thing that we're going to come up with is the number of valence electrons in each of these atoms. And you remember there are 2 different kinds of electrons? When we're drawing a shell structure of an atom, you have the valence shell and all the other shells that are called the core shells. What's the difference? Sean? Bingo. The valence shell is the outermost part. So if you think about an onion, it's the outermost skin on your onion, the one that you peel or add to when you're forming an ion, right? Okay, so let's take a look at lithium, all right? And if you want to think about the building analogy, think about like the floor that has, the highest level floor that has tenants in it, right? So here in lithium, what's the highest level fluor that has tenants in it? The second fluor. How many tenants are on the second fluor? So this has one valence electron. What about beryllium? Right? So it was those tenants there on that fluor. What about beryllium? What's the highest floor of the building that has tenants in it? The second floor. How many tenants are on that floor? 2. All right. Now, with boron, this is where students have an issue. What is the highest floor that has my tenants in boron? It's the second floor. How many tenants are on the second floor? There's 3 of them. All right. Some people tell me that the answer is 1. What mistake are they making? They're only counting the electron in the p orbital, but I want everybody on the second floor. I want those who are living in the p apartment as well as those who are living in the s apartment. So the answer really should be 3. What about carbon? Because we count what? The electrons that are in the s orbital as well as the electrons that are on the p orbital. So that's a total of 4 electrons. What about nitrogen? There's 5 because you count both the s's and the p's. How about oxygen? There's 6 because you count both the s's and the p's. How about fluorine? 7 because you count the s's and the p's. What about neon? 8. Wow, with enthusiasm. I love it. All right? Are we good so far? Fabulous. Okay. Now, all of these guys here, from lithium to fluorine, are they happy with that? No. What's wrong with them? They're not full, right? They're incomplete. Atoms don't like to stay like that in nature. What do they really want? A full shell. Now, what does it mean to be full? It depends on what period you're on, right? So if you're in the first period, these elements here, hydrogen and helium, bless you. Bless you. How many electrons does it take to be full in the first period? 2. Bless you. What about in the second period? It takes 8. What about in the third period? It takes 8. But what if you're down here? How many does it take? 18. All right, so these guys here from lithium to fluorine are not happy, right? Because their outermost shell isn't full. And so in nature, what they're going to do is turn into ions instead, all right? And so what are they going to do to become an ion? So over here on the left-hand side, again in my margin, I'm going to write, what does it take to fill the valence shell? Question mark. All right. So think about lithium, right? So if I have lithium, if I draw a shell model of it, it looks like this, right? So you've got 2 electrons in the first orbital, 1 electron in the second orbital. How many electrons can you actually put in that second orbital? 8. Lithium has a choice to make, right? It could choose to go out in nature and find 7 more electrons to put in that outermost ring to fill it, or it could lose that 1 electron that's there, thereby removing that outer skin and uncovering the one underneath that's full. What's easier? Losing 1 electron. So what lithium does is it loses 1 electron. What about beryllium? Why? Bingo. It loses 2 electrons because it's easier to lose 2 electrons than to gain 6. How about boron? And I'm drawing my shell models, and you should too. So what do we decide boron does? Loses 3, because again, it's easier to lose 3 than to gain 5 to fill that outermost layer. Okay, and then we get to carbon. It can be both. Why? Wait a minute, because it's in the middle. Because it's just as easy to lose 4 as it is to gain 4. So this loses or gains 4 electrons. It all depends on who it partners up with. If it partners up with someone who's got electrons to give up, it'll take them, and vice versa. All right? Well, what about, let's draw nitrogen real quick. How many valence electrons did we say nitrogen had? It had 1, 2, 3, 4, 5. What does nitrogen do? It gains 3 electrons. How about oxygen? Gains 2. Let me draw the shell. How about fluorine? With its 7 valence electrons. Let me see, 1, 2, 3, 4, 5, 6, 7. What does fluorine want to be full? Gain 1 electron. And what about neon? Our buddy neon, who's noble, doesn't do anything, right? Nobility does nothing. However, neon has the protons to pull electrons in, right? It's the best able in that series to pull electrons in. The problem is it doesn't have room, right? There's no room in the N to put those extra electrons. Are we good so far? This isn't anything new, is it? Okay, next. So what charge does the ion take when electrons are lost / gained? Do you remember we talked about how, I think the analogy I gave, not the most sensitive analogy, but we talked about like emos. When you gain an emo in the room, like you gain a new student in the room and they're kind of emotional, right? What do they do to the mood of the room? Sometimes, not always. They darken the mood of the room, right? And then when they lose, what happens to the mood of the room? It gets lighter, okay? So, what happens when you lose 1 electron? Does the mood of the room get positive or negative? It gets positive, right? Positive what? So, what should the formula be for lithium? So, what was the charge, first of all? It's 1 plus? So, what's the formula for that ion? Maybe we should add that to the bottom. How do you write that? Do you write Li 1 plus? Yeah? What about beryllium? When you lose 2 electrons, what is the charge that you end up taking? It's 2 plus. And then what's the symbol for that ion that you form? Be 2 plus? How about boron? When it loses its 3 electrons, what charge does it end up taking? 3 plus. What's the formula for the ion that you make? Be what? 3 plus. How about carbon? Ooh, this one's tricky. 4. Well, if it loses 4 electrons, what charge does it take? 4 plus. If it gains 4 electrons, what charge does it take? 4 minus, right? So it could be 4 plus or minus. So you could write carbon this way, or you could write carbon that way, depending on what element it decides to partner up with. All right, what about nitrogen? It's gaining electrons, right? So what's happening to the mood of the room? It's becoming more negative. So what is the charge going to be here for nitrogen? 3 minus. So what's going to be the symbol for that nitrogen ion? It's N3 minus, right? How about oxygen? What's the charge for oxygen? When you gain 2 more negative things, right, what's the overall charge of that? It's 2 minus. So the symbol for the oxygen ion is O2 minus. How about fluorine? What's the charge? 1 minus. And then neon? 0. Okay, so then the symbol for fluorine would be F1 minus, and then neon is Ne. Do I put a 0 in the corner? No, I don't have to. Right? It's understood. Okay, so I have my highlighter handy. You might want to have yours. I'm going to highlight that right there. And I'm going to write myself a little note. Memorize. I went through the whole rigmarole of giving you the electron configurations and drawing the dot structures, right, to give you the understanding as to why these charges are what they are. But at the end of the day, memorize them. Because it's going to be really critical when it comes down to naming. If you don't know how to name, if you don't know the charges for these things, you're not going to be able to write formulas. Okay? And then at that point, if you can't write a formula, then your stoichiometry, you won't be able to balance an equation, you won't be able to do any stoichiometry. So this is really uber critical. All right? So you know your little periodic tables? Take them out of the sheet protectors. And what I want you to do on the periodic table itself, on the top, right? What did we say? We said lithium had what charge? 1 plus? Right, 1 plus above that column. By the way, it's not just lithium that has a charge of 1 plus, all of its family members do too. Right? So everybody in this column has a charge of 1 plus. So just go ahead and write 1 plus on the top of that column. All right? What did we say about beryllium? What was the charge of beryllium? 2 plus. So we're going to go ahead and write a 2 plus on the top of that column on our periodic tables. We're going to ignore the transition metals. The transition metals don't play nice. All right? And we'll talk about what they do in just a little bit. Okay? What about boron? What's the charge of boron? So let's go ahead and write 3 plus on top of that column. What about the carbon column? What are we going to write above it? 4 plus or minus. How about the nitrogen column? 3 minus the oxygen column. 2 minus the fluorine column. And then the noble gas column? 0. Memorize them. Do you notice a pattern? First of all, they're all positive on the left-hand side, right? Because all metals are positively charged ions. There are negatives on the right-hand side, and basically what we're doing is we're counting up, 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 up till we get to carbon, right? 1, 2, 3, 4, count up, and then once you get to carbon, you count down. So 1, 2, 3, 4, 3, 2, 1, 0. All right? You have to have these suckers memorized. You can't write formulas without knowing these charges. All right? So far, so good? Okay, let's up the ante now. All of this should be review, right? This isn't anything new. Correct? All right, so let's make it a little bit more challenging now. Not a ton. And then depending on how things go with time, what we can do is I can give you a couple practice things, maybe give you 10, 15 minutes to start that first homework assignment, and then take a break, do a second set of notes, and then give you the rest of the class period to do the second homework assignment. Does that sound fair? If we can get things done in a quick amount of time, I can give you some time in class to work on that with me. Okay? All right. I don't want to totally take these off of the screen because I want to see these electron configurations. All right. But the next thing that we need to add to our table, one of the final things that we need to add to the table, is the electron configuration for the ion. scooch that down. So we're down here. All right, so let's start with lithium. So this was the original electron configuration for the atom of lithium, right? And what did we say lithium does in nature? It does what? Loses one electron. All right, so what electron does it lose? The 2s1 electron, right? So if you were to erase 2s1 from that electron configuration, what are you left with? All right, so we're just going to write helium. Let's see if you pick up on the pattern that's going to emerge. How about beryllium? That's the original configuration for the atom, right? So this guy loses 2 electrons. Which 2 electrons do you remove? Those in the 2s, right? So if I could erase that, if I could erase 2s2, right? What would be left? He. All right, what about boron? What do we say boron does? Loses 3 electrons. So if I were to remove those 3 electrons that are on that second floor, the 2 that are in the 2s and the 1 that's in the 2p, what would you be left with? He. All right, one more. Carbon. Well, let's start with just the He. Right, so if you were to lose those 4 electrons, right, you'd be left with He. All right, but Victor says He or Ne. How come? You could gain 4 electrons. If you were to gain 4 electrons, where would you put them? Do you have room in the 2p to put them in there? Right? And so if you put them in that 2p, you'd end up with helium 2s2 2p6, which is the same configuration as what? Neon. All right, let's take a look at the next one, nitrogen. What do we say it does? It gains 3 electrons. Where do I put those 3 electrons? Where's their room? Is there room in that 2s shell? No, because it's full. Is there room in the 2p shell? If I stick those extra 3 in the 2p shell, what is the configuration result as? It's helium 2s2 2p6, which is the same thing as neon. Do we have to go through the rest? Do you really want to? What about oxygen when it gains its 2 electrons? What configuration do you think it ends up with? Neons. And how about fluorine? Neons. And what about neon? Neons. All right, so let's draw a little arrow this way. What kinds of elements exist on the left-hand side of the periodic table? And I'm generalizing here. Metals. Okay. So metals form positively charged ions. Positive ions. And again, if you have a hard time remembering that, just remember the word metal has a T in the middle of it, T for positive, that look like noble gases in prior row. Now, that's not to say that they turn into that noble gas. On the inside, lithium is still lithium because the number of protons that it hasn't changed. It's just on the outside, it wants to look like helium. They're posers. They want to be like the cool kids, the noble gases. So they start dressing like the cool kids on the outside. But on the inside, the number of protons hasn't changed. What's up, Ron? Prior row. Right? So lithium here, right, wants to look like the noble gas that comes before it, that precedes it. So helium, right? What about these guys over here on the right-hand side? Are they metals or non-metals? Here, I'll scooch it up and zoom. Yeah, Sean? Say what? It's technically not right, because I should have written helium 2s2 2p6, right? I wrote it as neon that way on purpose so that you could see that from carbon on the outside, what they all wanted to look like is the noble gas that comes after. Okay? And that's what I want you to write on this other arrow. So non-metals form negative ions that look like noble gas on the same row. I'm overgeneralizing, Emily. Yeah. Well, because technically boron and carbon are metalloids. So this is kind of a gray area. Okay. Questions so far? Let's do a sample problem. I'm going to use a new sheet of paper. This is essentially your notes. You could flip to the back if you want to do these practice things. I'm just going to go to a new sheet of paper because my ink like bleeds through this paper. And if you want, you can turn it portrait now because I know it's uncomfortable to write landscape. So this is a little bit like the questions that you have to do on that first page that's assigned for homework tonight, which is page 214, right? So the first thing that you're going to have to do on page 214 is do questions 30, 32, 36, 60, 63. They're kind of like this, all right? And so what I'm going to ask you to do is to write the electron configuration for, let's say, P3 minus. Okay? I'm going to show you two ways of doing it. I'm going to show you the long-winded way and then the cheap way. All right? So let's start with the long-winded way. Okay, so the long way, number one, what I would do is I would write the configuration for the atom. So here's my periodic table, right? Oh, you can't see that. Bless you. We got to find phosphorus, right? Phosphorus is right there. And I'll forgive you. I mean, you guys are good now. I'll forgive you the long configuration. So from here on out, you can use noble gas, right? So what noble gas would I start with for this? I would start with neon. And then after neon, what do we read? What row is this? 3s2. And then we read over, what row is that? 3p3. Okay? And then the second thing that I do is I decide whether, if the charge tells me that I should be gaining or losing electrons. So decide if charge means gaining or losing. And this is where students usually have a tough time because when it comes to electrons, it's the opposite of what you think, right? So when you gain electrons here, normally you think of gaining as positive. The problem is that electrons are the negative bit. You're gaining negative things, right? So what does 3 minus mean? Okay, so that means you are adding 3 more electrons. So add 3 electrons, okay? All right, so then what you do is then you adjust your configuration for that, okay? Based on answer for step 2. All right, so you adjust your configuration based on that answer. All right, so then how would your configuration change? It would be neon, 3s2, and I can't put those 3 electrons in the s because how many electrons can you put in the s? 2 max, right? Where do you put those 3 electrons? Where? In the 3p3, and so the configuration would end up reading 3s2, 3p6. All right? What if you were losing electrons? What if you had to take away 3 electrons? Where would you take them away from? You would take them from 3p, and then if you still had to take more electrons away, where would you go to next? To the 3s. Okay? All right, now, so that's a long way. Let's do it the cheap way. What did I just tell you down here? What do metals do? What do? They form ions that look like noble gases in the prior row, right? What do nonmetals do? That look like in the same row. So guess what I'm going to do? I'm going to find phosphorus. Is it a metal or a nonmetal? Nonmetal. And so if it's a nonmetal, am I going to the row prior or to the same row? Okay, what does it look like? Argon. Period. Done. So the cheap way is just to remember that nonmetals form ions that look like noble gases in same row. Hey, what method's better? You guys like the long way or the cheap way? Cheap way. Of course you like the cheap way. No. Isn't this the same thing as that? But technically speaking, you wouldn't be able to write the configuration for argon that way. You technically would have to write it like that. Right? But if I would accept it either way. Okay. All right, so let's practice. So I want you to write the configurations for, let's see, aluminum 3+, let's think of another one, sulfur 2-, and this last one is hydrogen 1+, and this last one's tricky, okay? So see what you can come up with. And we decided we're going to do cheaper. Let's take a look at these answers. Let's start with aluminum. And again, I would never dare do any of this without a periodic table. All right? So if we look at aluminum, right, and I have to write the configuration for its ion, right? We know that things form ions in order to look like noble gases on the outside. So which noble gas are we talking about? Well, for you to be able to figure that out, you got to determine whether aluminum is a metal or a non-metal, correct? So what did we decide, metal or non-metal? What? It's a metal, right? Okay, so if it's a metal, does it look like the noble gas that comes before it or the noble gas that comes after it? Before it. So what's the noble gas that comes before aluminum? So you go up a row all the way over, it would be neon. So if you write neon, I'm good. Technically, that's not how you write the configuration for neon, but I'll be happy with that, Okay? All right, what about sulfur? Metal or non-metal? How do you know it's a non-metal? By the way, you can take your cues from the charges, can't you? If it's a positive charge, right, it's got a T in its name. Well, so does non-metal, doesn't it, right? Well, if it's a negative, it starts with an N, right? So positives are metals, negatives are non-metals. So what do we know about non-metals? Do they form same row, right? So what's on the same row as sulfur? Argon. Okay, hydrogen's a tricky question. Because if it's positive, it's going to be like the noble gas that comes in the row before it, right? Is there a row before it? No. So it's not going to end up looking like any noble gas, right? So how do you write the configuration for this? In this particular case, you're going to have to do it the long, old-fashioned way. Start with a configuration for the atom. So what is the configuration for the atom of hydrogen? It's 1s1. And what does 1 plus mean? You lost it, right? So if I get rid of that, what do I replace it with? A 0. So the configuration is 1s0. Okay? Tricky, right? But not impossible to do. All right. Let's talk about transition metals for a minute. Do a little practice question, and then I'll give you a good 15 minutes to do that page. And then we can talk about salts and ionic bonds. And the rest of the period is going to be like just taking notes. Okay. All right. So how do you write electron configurations for transition metals? That's the next thing that we're going to deal with. Transition metals, remember I told you that those aren't charges that you have to memorize. You have to memorize all these other ones, but not these. Transition metals are a real pain in the butt. And that's because they can actually have many charges. So for instance, we're going to do an example with vanadium in a second. Vanadium can exist as a +3, a +4, a +5. Iron, for instance, iron exists in 2 forms. So iron can either be +2 or it could be +3. It all depends on its mood. Actually, it has nothing to do with mood. It has to do with energy in the environment. All right? And so then, how do you write these configurations? Well, first of all, you have to understand what that means. What does 2+ mean? No. The opposite. And this is the important part. This is the part that students always mess up. What does 2+ mean? 2 fewer electrons. And what does 3+ mean? 3 fewer electrons. All right? So if I wanted to write the configurations for both of these things, I would start by writing the configuration for atomic iron, right? And we'll do it in noble gas notation. So iron is right there. It's in that 3D part of the periodic table. And I'm going to do this in noble gas. So the noble gas that comes before iron is argon. And if I start reading from argon, what's this next piece? And I'll scooch this down so you can see. So what row are we in? We're in the, which row? The 4th row. That's 4s, 2. And what comes after the 4s orbital? Be careful here. 3d. How many to get to iron? 1, 2, 3, 4, 5, 6. And I'm just going to start with that configuration. And I'm going to adjust it now for the fact that this guy has 2 fewer electrons and this guy has 3 fewer electrons. All right? So if I'm going to take 2 electrons away, and I want you guys just to put your pencils down for a second and watch, because this is the part where, again, people have issues. Where do I take those 2 from? Think about our building. When I go to empty the building, if I started putting the people in from the bottom floor and working my way up, when I empty my building, I go in the opposite direction, right? What was the highest floor of this building that had tenants? The 4th floor. So guess where I take them from? I'm going to take them from the 4s first. All right? So those 2 electrons you take away from the 4s. And so the configuration that you're left with is argon 3d6. All right? So I'll rewrite this over here. Argon 3d6. All right. What about if I take away 3 tenants from that building? Where do I take the tenants from first? Landon, I wouldn't put my head down, dude. This stuff is going to kill you. Where do I take them from first? I take them from the 4s floor first. Where do I take the 3rd electron from? After you empty out the 4th floor, then where can you go? To the 3rd floor. So where do I take that 3rd person from? From the 3d6. And so that would change to a 5. So then your configuration, I'll rewrite it again neatly on the right-hand side, would be argon 3d5. Okay? Let's practice. I want you to write electron configurations for vanadium, vanadium 3+, vanadium 4+, vanadium 5+. You can do this in double gas. Yes? You would. That's exactly what you would do. Okay, who needs more time? All right, so here's my configuration for the atom, vanadium. What does 3+ mean? Lose 3. Where do I take the first set of electrons from? I take them from the 4s, and then where do I take the 3rd one from? From the 3d, so what would that leave me with? It'd be argon 3d2. What about if I was 4+? Where would I take the 4th electron from? From that 3d2, leaving me with argon 3d1. And where would I take the 5th electron from? From the 3d, what would that result in? Argon. Now, technically speaking, that's not how you should write the noble gas configuration for argon. You really should go from neon, 3s2, 3p6, but it's okay. If you left that, I would be okay with that. All right? Okay, so I'm going to give you guys, let's see, 15 minutes to go ahead and start that page, that first page. And then I can certainly walk around. If you guys get done quicker than that, it's even better because we have a second set of